let's look at an idealized situation. You have a container, sealed container, that has water ice in it. You pull it from a freezer, let's say it's at minus 40 degrees Celsius. And you slowly apply heat to that container. An even heat. Say you put it in an oven and you have a small amount of heat constantly going into that container. Eventually, that ice will warm up. It will melt, become water. That water will then warm up, evaporate, and become steam, and then that steam will warm up, right? That the water vapor will warm up, as long as you continue to add heat to it. So I have here a diagram illustrating that. We have temperature here on the left-hand side, and we have time here on the right-hand, on the horizontal axis. So we start off pulling the ice from the freezer. It's at minus 40 degrees Celsius. Now, as you add heat, again, assuming that you add a constant amount of heat with time to this system, the ice will warm up. And that kind of is, not very intuitive for people. Most people think ice freezes 32 degrees Fahrenheit, 0 degrees Celsius, so ice should be 32 degrees Fahrenheit or 0 degrees Celsius. Absolutely not true, right? Steel melts at some ungodly temperature. That doesn't mean that steel, I forget the exact temperature, 3,000 something degrees or higher. So that doesn't mean that steel is at 3,000 something degrees. So whatever the temperature is of your freezer, if you leave water in there long enough, the ice that forms will reach that temperature. And if you ever thawed something out of a deep freezer, you know that you come back a little bit later, it still might be frozen. It's warmer, but it's still frozen. So with time, eventually the ice in that container will reach 0 degrees Celsius. So for a moment in time, all of the ice in that container, assuming gradual slow heat, and we're ignoring the fact that the outside of the ice might melt faster than the inside, or the temperature might change faster on the outside than the inside. Assume the heat is applied uniformly throughout the entire block of ice. That ice will begin to melt. Well, melting takes energy. Melting requires heat. But during that process of melting, the temperature doesn't change. So if I start with a 1 kilogram block of ice at 0 degrees Celsius, and I melt all of that ice, when I'm done melting that ice, I have 1 kilogram of water at 0 degrees Celsius. Well, the temperature hasn't changed. Both the ice before the melting and the water after the melting are the same temperature, but I still had to put heat into that system to get that ice to melt. So the equation we have for specific heat won't tell me how much heat is necessary to melt the ice, because the specific heat equation had a delta T in it, change in temperature. Here, there is no change in temperature during this phase change. All right, continuing on. Now we have water at 0 degrees Celsius. I continue to add heat. The water gets hotter and hotter and hotter until at 100 degrees Celsius, the water begins to boil. Liquid water is becoming water vapor, right? Gaseous water. That boiling process, again, I said it in a previous video, boiling is actually, you can think of it as a cooling process, because the water doesn't want to go above 100 degrees Celsius. So it basically creates water vapor to keep itself, the water, at 100 degrees Celsius. Well, liquid water becomes water vapor during the process of boiling. When you're done boiling away all of the water vapor you have is at 100 degrees Celsius. Again, this is another phase change from liquid to gas. Then, now you have gas trapped in this container, water vapor trapped in this container. Continuing to add heat will make the water vapor, or the steam, hotter and hotter and hotter. So if you want to know how much heat energy you need to go from a 1 kilogram block of ice, let's say, at minus 40 degrees Celsius, and you want to turn that into water vapor at, let's say, 120 degrees Celsius, 1 kilogram of water vapor, how much energy do you need to do that? How much heat do you need to add to the system? Well, we can figure out the sloped parts easily enough. This is the specific heat here. The heat is the specific heat of ice, of water ice, times the mass of that water ice, times the change in temperature. The change in temperature here is 40 Celsius degrees. The mass is 1 kilogram. We would need to look up the specific heat of ice, which your book gives you. Here, this, we know heat, we'll call this Q1. We don't know what Q2 is. Q3 is the heat needed during this process, heating up the water, which is the specific heat of water, times the mass of the water times the change in temperature. Here the mass of the water is still a kilogram. The mass throughout is going to be a kilogram. The temperature change is 100 Celsius degrees, or 100 Kelvin. And we need to look up the specific heat of water, which again is 4190 joules per kilogram Kelvin. And then finally we know, and we can figure out this slope, Q5 I'll call it, is equal to the specific heat of steam times the mass times the change in temperature. So Q1, Q3, and Q5, we can figure out the heats using our specific heat equation. Q2, oops, put over here, Q2, which is this melting process, and Q4, which is this boiling process, we don't have equations for that yet. Well, actually, I have them below if you're reading ahead. We need to figure out how much heat is needed to melt ice into water. We need to figure out how much heat is needed to evaporate, liquid water into a gaseous state. And that, during phase changes, the temperature doesn't change, so we call this the latent heat of transformation, because it's a phase transformation, right? It's going from a solid to a liquid or a liquid to a gas. So the heat depends on which transition you're doing. If you're melting or freezing, then you use what's called the latent heat of fusion, and the heat becomes L sub F times M. If you're boiling or condensing, then you use the latent heat of vaporization, L sub V, shown above. So this little thing here means pick one. You can either do this or do that. Q is equal to one of these two relationships, depending on if you're boiling, condensing, use the latent heat of vaporization. If you're melting, freezing, use the latent heat of fusion. And again, heat can be positive or negative. It depends on which way you're going. You have to add heat to go from a solid to a liquid. But if you're freezing something, right, you're taking heat from that system, so you go from a liquid to a solid. So you would have negative heat in that case. So going from a block of ice at minus 40 degrees Celsius to a block of steam, or not a block of steam, but steam, same amount of steam at 120 degrees Celsius, you would add heat to that system. To take 1 kilogram of steam at 120 degrees Celsius and turn to a block of ice at minus 40 degrees Celsius, you would have negative heat, right? You remove heat from the system. So this is really 5 steps to figure out how much heat is needed. You have to figure out specific heat at this point, latent heat of fusion here, specific heat and heat for water, latent heat of vaporization here, specific heat for steam. So the specific heat or the latent heat changes with each step, depending on the material. Again, water is the most common one we'll be using, and your book lists water for these things. This heat diagram then allows us to actually calculate, well, what happens if I have a thermos full of boiling hot soup? Say half a kilogram of boiling hot soup, and I drop an ice cube of minus 10 degrees, a 20-gram ice cube into that soup at minus 20 degrees Celsius. What is the final, assuming an insulated container, what's the final temperature of the soup? You can actually figure that out. Figure out how much heat is gained by the ice, which has to match the heat lost by the hot soup until those things balance and they reach equilibrium or the same final temperature. Now, one last thing, when dealing with latent heat of transformation or the specific heats, especially for you chemists out there, you might be more comfortable dealing with moles rather than kilograms. Here the mass is measured in kilograms. and here the mass is still measured in kilograms for the specific heat, you might be more comfortable with the molar specific heat, which gives the molar specific heat, you put the quantity in moles of the substance. That's a different number though, right? If you're more comfortable using the molar specific heat, that's up to you. Your book and I will be using the physics version, which deals with the mass in kilograms.